Good to have you here again. 10 years ago, someone used mathematics to figure out exactly what a piece of matter should look like, down to how its electrons would move and where. Nobody could build it. It only existed as a stack of equations on paper. This month, a team of physicists finally built it. They measured it, atom by atom, with a microscope precise enough to see individual bonds. And the numbers that came back matched the 10-year-old math almost exactly. The strange part isn't that they built it. The strange part is that we already knew what we'd find before it existed. Here's what actually happened, in plain terms. Physicists in Finland grew a crystal only 2 atomic layers thick, a material called tin telluride, on top of another crystal underneath it. That second layer squeezes the first one, ever so slightly, the way a slightly too small picture frame presses in on a photograph. That pressure turns out to matter enormously. Under that exact amount of strain, something happens at the very edge of the material that doesn't happen anywhere in its interior. Electrons can travel freely along the border in a kind of one-way lane, while the interior stays completely non-conductive. A material that is, at the same time, a conductor and an insulator, depending entirely on which part of it you're touching. This exact behavior, edges that conduct, interiors that don't, switchable by how hard you squeeze it, is not something the team stumbled onto. It's something theoretical physicists calculated should exist in a class of materials like this one, more than 10 years before anyone knew how to grow a crystal thin enough or clean enough to actually test it. For a decade, this was a shape with no material, an answer with no question attached to it yet. And here's the part that makes this stop being a one-off story. This isn't the first time physics has worked this way. It might be the most reliable trick in the entire field. In 1928, a physicist named Paul Dirac wrote down an equation to describe how electrons behave. The equation worked perfectly, except it also demanded that another particle exist, one nobody had ever detected. An electron's mirror opposite, carrying the same mass but the opposite charge. 4 years later, in 1932, someone found it in a cloud chamber, exactly where the math said it would be. 4 years is nothing. Here's where it gets strange. In 1964, a small group of physicists calculated that there had to be a particular kind of particle giving mass to everything else in the universe. Otherwise, the rest of the math simply didn't add up. It took until 2012, inside a 17-mile tunnel built specifically to look for it, before anyone actually saw it. Not 4 years this time. 48. And the longest gap of all belongs to Albert Einstein, who calculated in 1916 that massive objects colliding in space should send ripples through the fabric of space and time itself. Measurable, in theory, if you built an instrument sensitive enough. Nobody built that instrument for almost a century. 99 years. From a page of equations to a detector finally sensitive enough to feel the universe shake. 4 years. 48. 99. Every single time the math arrived first, fully formed, and reality simply took however long it needed to catch up. So maybe this is just a physics thing, a quirk of particles too small to see with the naked eye anyway. Except, nearly a century before any of those physics discoveries, the same exact pattern showed up in a completely different field, looking at something the size of a planet. In the 1840s, astronomers noticed that Uranus wasn't moving the way it should. Its orbit kept drifting slightly off from what the math predicted, as if something unseen out past it was tugging on it with its gravity. 2 mathematicians working independently in 2 different countries sat down with that discrepancy and calculated where an unknown planet would have to be to cause it. Not probably somewhere out there. A specific patch of sky. On the night of September 23, 1846, an astronomer in Berlin pointed a telescope at those exact coordinates. Neptune was there, within about 1 degree of where the equation said it would be. Nobody had seen this planet. Nobody had a telescope powerful enough to have noticed it by accident. It was found because 2 people trusted a page of arithmetic enough to point a telescope at an empty-looking sky, and it was waiting for them. It happened again, 1 field over, 23 years later, and this time, nobody was even looking for a single missing object. They found a missing shape. In 1869, a chemist named Dmitri Mendeleev was arranging every known element by weight and behavior, trying to find the pattern underneath the periodic table. Partway through, the pattern broke. There were gaps, spaces where an element should sit based on everything around it, except no such element had ever been found. Most people would have assumed the pattern was wrong. Mendeleev did the opposite. He left the gaps in on purpose and wrote down, in advance, what the missing elements would weigh, how they'd react, even what color they'd likely be. 6 years later, in 1875, a chemist in France isolated a new element. Its properties matched one of Mendeleev's empty boxes almost exactly. 11 years after that, a second gap was filled the same way. The table wasn't describing what chemists had already found. It was describing what had to exist, whether or not anyone had found it yet, the same way an unseen planet had to exist, and the same way an untested material had to conduct electricity only at its edges. None of these are stories about brilliant guesses. A guess can be wrong. What's actually happening every time is closer to this. Certain structures in mathematics don't describe reality after the fact. They describe a space reality hasn't filled in yet, and eventually, whether it takes 4 years or 4,000, something moves into it. We don't build these things and then understand them. And this is not, it turns out, a modern habit at all. More than 2,000 years before anyone understood gravity, before anyone had a word for an electron, let alone an equation for one, astronomers in ancient Mesopotamia were pressing marks into wet clay, tracking the sky closely enough to notice something remarkable. Eclipses weren't random. They repeated on a cycle lasting almost exactly 18 years, 11 days, and 8 hours. They had no idea why. They didn't know the moon orbits the Earth, or that the Earth orbits the sun, or anything about the physics involved. What they had was a pattern in the numbers, pressed into tablets that would outlast their entire civilization, and they trusted that pattern enough to write down, in advance, when the sky would go dark again. They were right, over and over, for centuries, using nothing but arithmetic, aimed at a sky they didn't yet understand. The tools have changed almost beyond recognition since then. Clay tablets became telescopes. Telescopes became particle colliders, and gravitational wave detectors and microscopes that can see individual atoms bend under strain. But the habit underneath all of it hasn't moved an inch. Which brings us back to a 2-layer crystal, squeezed just slightly out of shape, in a lab in Finland. 10 years ago, it was a page of equations nobody could test. Today, it's sitting under a microscope, doing exactly what that page said it would do. Its edges alive with electrons, its interior silent, exactly on schedule. We don't build these things and then understand them. We understand them, and then, eventually, we build them. Not every gap in the math gets filled this quickly. Some are still sitting there, waiting. I'm Leo, this is Pattern Notes. We gather here, and stories pass through us. This was one of them. See you next time.